So continuing with polynomials, there exists something called the remainder theorem. And the remainder theorem says this, that for a polynomial, we'll call it f of x, if we are dividing f of x, this polynomial divided by a binomial, x minus c, right? So this is 1x to the first power minus some number c, then we can quickly find the remainder. Without actually doing the division, we can quickly find the remainder simply by plugging in this number c into f and evaluating f of c. Right, so here's what happens. Let's find the remainder here before we jump into the next part. Let's find the remainder here of, this is going to be x to the third plus 7x squared minus 19x plus 2 divided by x plus 4. So since this says x plus 4 and our theorem says x minus a number, that means this is equivalent to, let's use blue over here. That means this is equivalent to x minus negative 4. So what we're doing here to evaluate the remainder is going to be evaluating f of negative 4. That means negative 4 to the third power plus 7 times negative 4 squared minus 19 times negative 4 plus 2. Now you can plug all this into your calculator. If you want to evaluate it one by one, we're going to use order of operations. That's a negative 64 plus 7 times a positive 16 minus 19 times negative 4 plus 2. Doing the multiplication now, we're going to get a negative 64 plus 112 plus a 76 plus 2. And adding this together, we're going to get a positive 126, right? So that means that if we were to actually do this division, right, this remainder theorem does not tell us what the quotient is going to be, but it does tell us that the remainder is equal to 126, right? That's all the remainder theorem tells us. Now let's do another one before we jump into why this remainder theorem is a nice thing. Let's look at the same function, x to the third plus 7x squared minus 19x plus 2. This time we're going to divide it by x minus 2 and see what the remainder turns out to be. So that means we are evaluating here f of 2. Right? So again, x plus 4 means that we're evaluating a negative 4 in here. X minus 2 means we're evaluating f of 2. Right? So that's going to be 2 raised to the third power. Let me write that again. Plus 7 times 2 squared minus 19 times 2 plus 2, that's 8, plus 7 times 4 minus 28, not 28, minus 38 plus 2. That's going to be 8 plus 28. Oh, did the multiplication too soon, but you know, it was outside of exponents, so it's fine. And we're going to add these up, and we're going to get a remainder of 0. So the remainder here equals 0. So here's the second part of the remainder theorem, which says that if f of c, evaluating this, actually turns out to be 0, that means that the binomial x minus c is a factor of f of x, right? So based on our findings here, x plus 4 is not a factor of x to the third plus 7x squared minus 19x plus 2, right? Our original polynomial. But since we got a remainder of 0, that means that x minus 2 is a factor of x to the third plus 7x squared minus 19x plus 2. And the reason is the remainder is 0, right? because remainder is equal to 0. Right here, because the remainder is not 0, right? The remainder is not, if it's anything other than 0, doesn't matter if it's positive or negative, how small or large, if it's not 0, that means the binomial it came from is not a factor. Right, and that's all the remainder theorem says. So let's combine this with something called the rational roots test. And here's what the rational roots test says. Right, if we were looking at a polynomial that began with ax to the nth power plus bx to the n minus 1 and so on and so forth, and ended up with a constant c at the end, right, here's an example of that, 2x to the third plus 3x minus 5. Right, that means if we are looking for roots, we're looking for locations where this graph of this polynomial is going to cross the x-axis. But we're looking for maybe this equation set equal to 0 and those answers. Right, this thing that's called the rational roots test, or rational roots, also known as the rational roots theorem. Right, this says that possible, not definite, but possible roots that are rational functions, that are rational numbers, right? Not irrational numbers. This is not going to help us find the radical numbers, but it is going to help us find those whole numbered roots, those integer roots, those maybe fractional roots, right? So possible rational roots are this fraction, which consists of the factors of the constant term and over the factors of the leading coefficient, right? So those two numbers, right? Let's take a look at this example. The leading coefficient is equal to 2. The constant number is equal to 5. And as far as the rational roots theorem is concerned, this stuff in between doesn't matter, right? All we're concerned about is these numbers here, 2 for A, and this should be a C. -5 for C. Now we're going to take the factors of this, -5. So factors of -5 are going to be 1 and 5. That multiplies to 5. But remember, this is a -5, and whether this C value is negative or positive, we do have to consider that maybe 1 is a negative number or maybe 5 is a negative number. Right? Because one of them has to be negative in order to multiply up to -5. So this is going to be a fraction. And on the denominator of this fraction are the factors of 2. Now, what multiplies to get 2? That's 1 and 2. But remember, multiplying to get positive 2 means that either both of these numbers are positive or both of them can be negative. So when we are figuring out the factors here, we do have to consider both the positive and negative numbers that make it up. And this is going to create a list of possible rational roots for us. One of them is going to be 1 over 1, right? That is 1 here over 1 here. Another one is going to be -1 over 1. That's this -1 divided by this +1. Right? In addition to that, we're going to have possibly 5 over 1. That's +5 here divided by a +1 here. Or 5 can be a negative number, right? So these are some possibilities of roots that are rational numbers, right? Are they definite? Is it definite that 5 over 1 is going to be a root? No, it's not. It's a possibility. But in addition to this, we can have all of these same numerators, 1, -1, 5, and -5. And on the denominator, this same 1 except negative. So this is all of the possibilities of these numerators, these four numerators here, 1, -1, 5, -5, over these two denominators here, +1 and -1. Now we have two more denominators to worry about. That's a +2 and a -2. So let's look at the +2 first. We have four different numerators. That's 1, -1, 5, and -5. And if we put these over this same denominator of +2, that gives us four more possibilities. Again, the same four numerators. That's 1, -1, 5, -5 on the numerator, and our very last fourth denominator here, which is -2. So in total, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 possibilities, 16 possible rational roots. Now what this is saying is, for instance, is it possible that the number 3 is a root here, right? If we were to find a root, we were to try to find a root, we would pick, maybe, and evaluate f of 3, f of 2, f of 1, maybe f of 4, f of 5, f of 6. Where does this stop? And the answer is it kind of doesn't. But what the rational root test, rational root theorem tells us is that, you know what, 6's don't even bother. Number 3 here, 2 over 1, 4 over 1. Don't even bother with these. 5 over 1, maybe. 1 over 1, maybe. Right, let's take a look. Do we actually have 16 different numbers over here? Right, the first number we have is a 1. That's right there. I'll write this in blue. Right, that's a unique number, 1. Over here, -1, 5, and -5, right? And the fact that they're over 1 is just the result of our setup. Now look at these numbers here on the right-hand side. 1 over 1 is equal to -1. We got that already. -1 over -1 is +1. That's over there. 5 over -1, well, that's covered over here with -5. -5 over -1, that's covered over there. So in fact, we have some duplicates here, right? All of these numbers here are duplicates. Is it always going to work out that way? No. Which is why we have to write them down and determine whether they indeed are duplicates. And let's look at the next row. Do we have any new numbers coming out of that second row? Right over here, 1 over 2, -1 over 2, 5 over 2, -5 over 2. Have we written those down in blue just yet? No, we haven't, so let's write those down. And let's look at the next half of this row, -1/2. We got that there. This will evaluate to a +1/2. That's over there. 5 over -2. That's a -5 over 2 right there. And negative over negative is a positive, so this is covered already. So in fact, also duplicates here. So these are all the possible roots. These are all the possible rational roots. Now, is it possible that there are irrational roots? You know, something along the lines of 2 plus radical 3? Yes. This test does not consider that, right? Using this theorem, there's no way to figure that out, right? There's other things that we can use to figure that out. But this will give us a starting point if we are looking for a root which will lead to a factor, something like f of -1. Let's try f of 5. Let's try f of 1, right? Right, and these are probably I would say the easiest numbers out of this crew. Let's copy this over here. This is our f of x. So let's look at f of 1, right, to begin with. That's 2 times 1 to the third power plus 3 times 1 minus 5. Right, so 1 to the third power is equal to 1 plus 3 times 1 minus 5. That's equal to 2 plus 3 minus 5, right? 2 times 1, 3 times 1. This is equal to 0. So look what happened. We found a remainder of 0 when we were evaluating this f of 1. And what does that mean? Therefore, this means that x minus 1, again stemming from this number here, x minus 1, is a factor of 2x to the third plus 3x minus 5, right? And plugging in, evaluating f of 1, getting the remainder of 0 is exactly what tells us that. My cat's breath smells like cat food. So let's take this f of x again. Let's try f of 5, right? Let's see if 5 turns out to get a remainder of 0. That's going to be 2 times 5 to the third power plus 3 times 5 minus 5. That's going to get us 2 times 125 plus 3 times 5 minus 5. That's going to equal 250 plus 15 minus 5. Right, if we add this up, 250 plus 15, 265. Subtract 5, we get 260. And again, this is the remainder. So that means this binomial, x minus 5, therefore, x minus 5 is not a factor of 2x to the third plus 3x minus 5. Now, again, this rational root test does not tell you definitively that these are the roots. It tells you that these are possible roots. All right, it's what this is a process to narrow down the number of possibilities that we can test in here. Right, again, f of 2 is not going to be possible. We already know that's eliminated from discussion. F of 5 was possible. It turns out it's not based on this remainder. Right, so let's try one more. This is going to be a big one, so we can see how big this rational root test gets when these numbers are not prime numbers like we just saw, right? So a is equal to 6 and c is equal to negative 30. So let's write out the factors of c, rather. Factors of negative 30 are 1, 2, 3, 5, 6, 10, 15, and 30. But remember, again, the real nasty thing here, and it's just going to be long, that's just the way it is that these are positive or negative. And then the denominator, we're going to have the factors of 6. That's 1, 2, 3, and 6. Positive or negative, once again. So a lot to handle here. 1 over 1. So if we look at this right here, 1 over 1, 2, 3, not 4, 5, 6, 10, 15, 30. All of that over a denominator of 1. All right, once again, the same numbers, 1, 2, 3, 5, 6, 10, 15, 30, all of those with a denominator of -1. So what we're doing here in order to write out every single possibility based on this is you have to write out every single number in the denominator, in the numerator, with every single number in the denominator, right? Every single number in the numerator and every single number in the denominator. So I wrote out all of these. I wrote out all of these numerators over 1. Now I've got to write out all of these negative numerators over 1. And I have to do the same thing again. 1 over -1, 2 over -1, 3 over -1, 5 over -1, 6 over -1, 10 over -1, 15 over -1, 30 over -1. -1 over -1, -2 over -1. This gets very large very quickly, so hopefully you won't have an example quite as extreme as this. Because not only do I have to, because all of this here only represents these numbers with a denominator of 1 or -1, right? There's still going to be more with 2, -2, 3, -3, and 6, -6. And you get a whole lot of possibilities, but you also get a whole lot of eliminations, right? So if you do, like it turns out that, all of these here are going to be some form of duplicates of this. So you will get a whole lot of duplicates, right? But you will still end up with a long, very long list of factors after you have basically taken out all of the duplicates. You will still get a long list of numbers, significantly longer than the last problem, right? But again, that's the nature of this kind of problem, which is you have a long list of numbers, and this is going to end up with 1, 2, 3, 5, 6, 10, 15, and 30 as possible rational roots, in addition to 1 over 2, 3 over 2, 5 over 2, 15 over 2, 1 over 3, 2 over 3, 5 over 3, 10 over 3, 1 over 6, and 5 over 6. Right, so this is going to be your final list of possible rational roots, but positive or negative, all of these. So a lot. Still less than the infinite amount of numbers there are in existence. Right, so yes, it's going to be a lot, but this is also still an exercise in narrowing things down, right? The field is still smaller. However big this field is, it is still smaller than the infinite possibilities without doing this exercise. Right, so thank you for watching, and I will see you